Machine learning relies on an intricate web of mathematical dependencies. Within this labyrinth, every node and connection influences the final result, measured as the cost. To improve the network, we must determine exactly how sensitive that final cost is to an adjustment in one specific weight. This sensitivity tells us how to step toward a lower error. We represent this as a partial derivative. Specifically, it is the ratio between a tiny nudge in a weight and the resulting change in the cost. To see the mechanics clearly, we'll start with a constrained one-neuron system. This isolates the calculus before we scale back up to a full matrix architecture. This localized calculation serves as the foundational logic for the entire optimization process. We'll begin with a network where every layer contains exactly one neuron. This removes the noise of complex indexing. Look at the very last connection. We have a final weight, a final bias, and the activation from the previous layer. These three parameters combine into a single term, the weighted sum, which we label z. This z value is then pumped through a nonlinear function, like a sigmoid or ReLU, to produce the final activation output, a. We then generate the final cost by comparing this output activation to the desired target value, y. We can visualize this as a chain of local number lines. A small nudge to the weight triggers a ripple through z, then a, finally reaching the cost. Because of this structure, changes in the cost are never directly linked to a weight. They are filtered through this specific sequence of dependencies. The chain rule is the direct mathematical translation of this sequence. It requires us to multiply three local ratios to find the final sensitivity. The first component is the derivative of the cost with respect to the final activation. For a squared error, this is simply 2 times the difference between a and y. This means the sensitivity of our error scales with the distance between what the network guessed and what we wanted it to see. The second component is the derivative of the activation with respect to z, which is just the geometric slope of our activation function. The third component, the derivative of z with respect to the weight, evaluates simply to the previous activation. This reveals something intuitive. The weight's influence on the current layer is determined by how strongly the previous neuron is firing. If we were solving for a bias instead of a weight, this final local derivative would simply be 1. Multiplying these three localized derivatives gives us the exact sensitivity of the overall cost to a tiny change in that single weight. To move deeper into the network, we shift our focus from the weight to the activation of the previous layer. We need to know how sensitive the cost function is to this previous activation so we can continue the chain. We calculate this by swapping our final local derivative for the derivative of z with respect to the previous activation. That sensitivity evaluates to the value of the connecting weight itself. This result becomes the starting value we need to analyze the weights and biases in the preceding layer. We then must apply the exact same 3-part formula recursively. This process moves continuously backwards from right to left, illuminating the sensitivities of each previous layer in sequence. Backpropagation is simply this localized chain rule repeated recursively through the graph. Most networks aren't a single line. They are a matrix of many neurons per layer. We use index k for the previous layer and j for the current layer to track these connections. The local chain rule for any single specific weight remains identical to our one-neuron model. However, the calculation changes when we look at the sensitivity of the cost to an activation in the previous layer. In this architecture, neuron K influences the final cost through multiple independent paths simultaneously, branching out to every neuron in the next layer. According to the rules of multivariable calculus, we must account for the effect passing through every possible path. To find the total sensitivity, we must add up the individual chain rule derivatives across all those connecting paths. This summation is what distinguishes backpropagation in deep learning from standard single-variable calculus. Even with this added layer of complexity, we are still only looking at the derivative for one training example. The core logic of the calculus remains the same. We are simply aggregating local effects across branching paths. A real network evaluates its performance over thousands of different examples. To find the true derivative for a weight, we must average our multipath chain rule results across that entire dataset. This brings us back to the massive gradient vector. Each average derivative we calculate forms just one coordinate within that vector. The scale is massive. We are executing this localized derivation for millions of weights and biases simultaneously to build the complete gradient. This assembled vector provides the exact coordinates needed to minimize the cost. All of these massive computations allow the neural network to navigate the complex mathematical landscape, minimizing cost by stepping precisely downhill. Ultimately, backpropagation is the systematic application of the multivariable chain rule to track these path dependencies through the computational graph.